Hello friends, today we are going to start a new and very interesting topic, that is relativity. It is the field of physics that measures events, things that happen, where and when they happen, and by how much any two events are separated in space and in time. In addition, relativity has to do with transforming such measurements between reference frames that move relative to each other. Transformations and moving reference frames, such as those we discussed in earlier lectures, were well understood and quite routine to physicists till 1905. Then Albert Einstein published his special theory of relativity. The adjective special means that the theory deals only with inertial reference frames, which are frames in which Newton's laws are valid. Starting with two deceivingly simple postulates, Einstein stunned the scientific world by showing that the old ideas about relativity were wrong, even though everyone was so accustomed to them that they seemed to be unquestionable common sense. This supposed common sense, however, was derived only from experience with things that move rather slowly. Einstein's relativity, which turns out to be correct for all physically possible speeds, predicted many effects that were at first study bizarre because no one had ever experienced them. In particular, Einstein demonstrated that space and time are entangled, that is, the time between two events depends on how far apart they occur and vice versa. Also, the entanglement is different from observers who move relative to each other. One result is that time does not pass at a fixed rate, the rate is adjustable. Relative motion can change the rate at which time passes. Prior to 1905, no one but a few daydreamers would have thought that. Now engineers and scientists take it for granted because their experience with special relativity has reshaped their common sense. For example, any engineer involved with the global positioning system must routinely use relativity to determine the rate at which time passes on the satellites, because the rate differs from the rate on Earth's surface. If the engineers failed to take relativity into account, GPS would become almost useless in less than one day. Galilean relativity. To describe a physical event, we must establish a frame of reference. An inertial frame of reference is one in which an object is observed to have no acceleration when no forces act on it. Furthermore, any frame moving with constant velocity with respect to an inertial frame must also be an inertial frame. There is no absolute inertial reference frame. Therefore, the result of an experiment performed in a vehicle moving with uniform velocity must be identical to the results of the same experiment performed in a stationary vehicle. The formal statement of this result is called the principle of Galilean relativity. That is, the laws of mechanics must be the same in all inertial frames of reference. Let us consider an observation that illustrates the equivalence of the laws of mechanics in different inertial frames. The pickup truck in figure moves with a constant velocity with respect to the ground. If a passenger in the truck throws a ball straight up and if air effects are neglected, the passenger observes that the ball moves in a vertical path. The motion of the ball appears to be precisely the same as if the ball were thrown by a person at rest on the earth. The law of universal gravitation and the equations of motion under constant acceleration are obeyed when the truck is at rest or in uniform motion. Consider also an observer on the ground as in figure B. Both observers agree on the law of physics. The observer in the truck throws a ball straight up and it rises and falls back into his hands. The observer on the ground sees the path of the ball as a parabola, whereas, as mentioned earlier, the observer in the truck sees the ball move in a vertical path. Furthermore, according to the observer on the ground, the ball has a horizontal component of velocity equal to the velocity of the truck. Although the two observers disagree on certain aspects of the situation, they agree on the validity of Newton's laws and on such classical principles as conservation of energy and conservation of linear momentum. This agreement implies that no mechanical experiment can detect any difference between the two inertial frames. The only thing that can be detected is the relative motion of one frame with respect to the other. Galilean transformation equations. Suppose some physical phenomena which we call an event occurs and is observed by an observer at rest in an inertial reference frame. The wording in a frame means that the observer is at rest with respect to the origin of the frame. The event's location and time of occurrence can be specified by the four coordinates x, y, z and t. We would like to be able to transform these coordinates from those of an observer in one inertial frame to those of another observer in a frame moving with uniform relative velocity compared with the first frame. Consider two inertial frames S and S prime. The S prime frame moves with a constant velocity v along the common x and x prime axis, where v is measured relative to S. We assume the origins of S and S prime coincide at t is equal to 0 and an event occurs at point P in space at some instant of time. For simplicity, we show the observer O in the S frame and the observer O prime in the S prime frame as blue dots at the origins of their coordinate frames, but that is not necessary. Either observer could be at any fixed location in his or her frame. Observer O describes the event with space-time coordinates x, y, z and t, whereas observer O prime in S prime uses the coordinates x prime, y prime, z prime and t prime to describe the same event. As we see from geometry in figure, the relationship among these various coordinates can be written as x prime is equal to x minus v t, y prime is equal to y, z prime is equal to z and t prime is equal to t. These equations are the Galilean space-time transformation equations. Note that time is assumed to be the same in both inertial frames, that is, within the framework of classical mechanics, all clocks run at the same rate regardless of their velocity. So, the time at which an event occurs for an observer in S is the same as the time for the same event in S prime. Consequently, the time interval between two successive events should be the same for both observers. Although this assumption may seem obvious, it turns out to be incorrect in situations where v is comparable to the speed of light. Now, suppose a particle moves through a displacement of magnitude dx along the x-axis in a time interval dt as measured by an observer in S. It follows from equations that the corresponding displacement dx prime measured by an observer in S prime is dx prime is equal to dx minus v dt, where S prime is moving with speed v in the x direction relative to frame S. Because dt is equal to dt prime, we find that dx prime over dt prime is equal to dx upon dt minus v, or u prime x is equal to ux minus v. Here ux and u prime x are the x components of the velocity of the particle measured by observers in S and S prime respectively. We use the symbol u rather than v for particle velocity because v is already used for the relative velocity of two reference frames. The equation derived here now is the Galilean velocity transformation equation. It is consistent with our intuitive notion of time and space, but we shall soon see, however, it leads to serious contradictions when applied to electromagnetic waves. Speed of light. It is quite natural to ask whether the principle of relativity also applies to electricity, magnetism and optics. Experiments indicate that the answer is no. Maxwell showed that the speed of light in free space is 3 into 10 raised power 8 meters per second. Physicists of the late 1800s thought light waves move through a medium called the ether, and the speed of light is c only in a special absolute frame at rest with respect to the ether. The Galilean velocity transformation equation says that if light travels along the x axis and an observer moves with velocity v along the x axis, the observer measures the light to have speed c plus minus v, depending on the direction of travel of the observer and the light. Earth as a moving frame. Because the existence of a preferred absolute ether frame would show that light is similar to other classical waves and that Newtonian ideas of an absolute frame are true, considerable importance was attached to establishing the existence of the ether frame. Prior to the late 1800s, experiments involving light traveling in media moving at the highest laboratory speeds attainable at that time were not capable of detecting differences as small as the difference between c and c plus minus v. So, scientists decided to use the earth as a moving frame in an attempt to improve their chances of detecting these small changes in the speed of light. Observers fixed on the earth can take the view that they are stationary and that the absolute ether frame containing the medium for light propagation moves past them with speed v. Determining the speed of light under these circumstances is similar to determining the speed of an aircraft traveling in a moving air current or wind. Consequently, we speak of an ether wind blowing through our apparatus fixed to the earth. The Michelson-Morley experiment. The most famous experiment designed to detect small changes in the speed of light was first performed in 1881 by A. Michelson and later repeated under various conditions by Michelson and Edward W. Morley. As we shall see, the outcome of the experiment contradicted the ether hypothesis. The experiment was designed to determine the velocity of the earth relative to that of the hypothetical ether. The experimental tool used was the Michelson interferometer as shown in this figure. First, we shall understand its working. The interferometer splits a light beam into two parts and then recombines the parts to form an interference pattern. The device can be used to measure wavelengths or other lengths with great precision because a large and precisely measurable displacement of one of the mirrors is related to an exactly countable number of wavelengths of light. A ray of light from a monochromatic source is split into two rays by mirror M0, which is inclined at 45 degrees to the incident light beam. Mirror M0, called a beam splitter, transmits half the light incident on it and reflects the rest. One ray is reflected from M0 to the right towards mirror M1 and the second ray is transmitted vertically through M0 towards mirror M2. Hence, the two rays travel separate paths L1 and L2. After reflecting from M1 and M2, the two rays eventually recombine at M0 to produce an interference pattern which can be viewed through a telescope. The interference condition for the two rays is determined by the difference in their path length. When the two mirrors are exactly perpendicular to each other, the interference pattern is a target pattern of bright and dark circular fringes. As M1 is moved, the fringe pattern collapses or expands depending on the direction in which M1 is moved. For example, if a dark circle appears at the center of the target pattern corresponding to destructive interference and M1 is then moved a distance lambda by 4 towards M0, the path difference changes by lambda by 2. What was a dark circle at the center now becomes a bright circle. As M1 is moved an additional distance lambda by 4 towards M0, the bright circle becomes a dark circle again. Therefore, the fringe pattern shifts by 1/2 fringe each time M1 is moved a distance lambda by 4. The wavelength of light is then measured by counting the number of fringe shifts for a given displacement of M1. If the wavelength is accurately known, mirror displacements can be measured to within a fraction of the wavelength. Now, to determine the velocity of the earth relative to that of a hypothetical ether, we shall use the same experiment, but drawn in a different way as shown here. To determine the velocity of the earth, the arm 2 is aligned along the direction of the earth's motion through space. The earth moving through the ether at speed v is equivalent to the ether flowing past the earth in the opposite direction with speed v. The ether wind blowing in the direction opposite the direction of the earth's motion should cause the speed of light measured in the earth frame to be c minus v as the light approaches mirror M2 and c plus v after reflection, where c is the speed of light in the ether frame. The two light beams reflect from M1 and M2 and recombine and an interference pattern is formed. The interference pattern is then observed while the interferometer is rotated through an angle of 90 degrees. The rotation interchanges the speed of the ether wind between the arms of the interferometer. The rotation should cause the fringe pattern to shift slightly but measurably. Measurements failed, however, to show any change in the interference pattern. The Michelson-Morley experiment was repeated at different times of the year when the ether wind was expected to change direction and magnitude, but the results were always the same. No fringe shift of the magnitude required was ever observed. The negative results of the Michelson-Morley experiment not only contradicted the ether hypothesis but also showed that it is impossible to measure the absolute velocity of the earth with respect to the ether frame. Einstein, however, offered a postulate for his special theory of relativity that places quite a different interpretation on these null results. In later years, when more was known about the nature of light, the idea of an ether that permeates all of the space was abandoned. Light is now understood to be an electromagnetic wave which requires no medium for its propagation. As a result, the idea of an ether in which these waves travel became unnecessary. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. In this lecture, we learnt that an inertial frame of reference is one in which an object is observed to have no acceleration when no forces act on it. Galilean relativity states that the laws of mechanics must be the same in all inertial frames of reference. Following the negative outcome of the ether drift experiments like the Michelson-Morley experiment, the concept of ether as a mechanical medium having a state of motion lost supporters. It has been replaced in modern physics by the theory of relativity given by Albert Einstein. So that is it for today. In the next lecture, we shall be talking more about relativity. Thank you very much.